First off, I want to say that we're hopefully going to finish all the new material that you'll need for exam 3 today. Remember, exam 3 is a week from yesterday. A week from yesterday. And so if you want to sign up for the conflict exam, you have to do that by Friday. And it's going to cover chapters 12 through 18. And we're going to hopefully finish 18 today. So what are we going to do for 2 days then? We'll have Thursday of this week, and then Tuesday, we'll spend 2 weeks going over reviewing for the, not 2 weeks, 2 classes reviewing for the exam. All right, that's if we finish up in this lecture, and we probably will. All right, now we did leave off right here in chapter 17, page 191. And remember, we talked about this amazing idea here that we were thinking of sampling as tasting. And that was the intuitive way to explain this really amazing idea that as long as the sample is only a small part of the population, then only the size of the sample determines the accuracy of our estimate, not the size of the population. So in other words, like a sample of 1,000 randomly drawn from the entire US population, or from, let's say, a sample of 1,000 drawn from U of I, and the sample of 1,000 drawn from the entire US would be about the same level of accuracy. So you'd think you'd need a bigger sample for a larger population, don't you? Don't you think you'd have to sample more people if we wanted to estimate what everybody in the US thought about something rather than just people at the U of I, what they thought about something? Wouldn't you? And you really, what this formula says, what this statement says is that you don't. Because 1,000 people would be a small fraction of all U of I students, and 1,000 people is a small fraction of the entire US. It's a smaller fraction, but it hardly matters. And we didn't go into the math of it, but here, let's look at this, okay? So it's actually slightly more accurate. The population size does matter a little bit. According to this formula here, like the standard error formula, SD divided by the square root of n. The square root of n is only the sample size, right? That formula depends on if you're sampling with replacement. Because then your population size doesn't matter, right? Because you're sampling with replacement. So even if you have 2 tickets, like a 1 and a 0, if you put back, you have a 50-50 mix of 1s and 0s, you only have to have 1 1 and 1 0, because you're putting back the ticket, so you'll always have, it doesn't matter. But when we take a sample, a survey, we're always sampling without replacement. It's not like a gambling game. So we really can't, our formula changes slightly. Sampling without replacement is going to be slightly different. And there's actually a different formula. You multiply by this correction factor right here. Okay? Now, why would sampling without replacement be different than sampling with replacement? Well, obviously, it's going to lower, think about it. If you're sampling without replacement, what if you sampled the whole population? What if you had, the population was 2,000 people, and your sample was, you kept drawing without replacement, and if you sampled the whole population, you'd have no error. Every single time your sample would be the same as the population because it would be the population. Right? And if you sample the whole population, you're going to have, it's like a census. There's not going to be any error. You just have exactly what the population is. But, so obviously, if you could have no error. So your standard error is going down, getting smaller and smaller, the bigger your sample, but it's by this factor. So in an example where you're sampling like 1,000 people from the whole United States, this is your sample size, this is your population size, it's almost exactly the same thing. It's a fraction, tiny, 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 tiny bit smaller, but it hardly makes a difference. And so when the sample size is small, it's so close to 1 that you can pretty much ignore it. But what if the sample size is larger? Like, at what point would we have to use this correction factor? At what point would we have to? Let's think about it. Let's say the sample was as large as 20% of the population. As large as 20% of the population. What would this correction factor be? So this would be 20%. So imagine like 100% minus 20%, minus 20%. So you'd have 80 in the numerator over almost 100 minus almost 100. So you'd have like the square root of 80, which would be about, 90%. So even if you're sampling as much as 20%, like 1/5 of all the people, you're still only lowering your standard error by, you're just taking 90% of your standard error. So we can call that the cutoff for this class. Even if the sample is as large as 20% of the population, it's hardly ever that large as 20% of the population. We're not going to bother with the correction factor. All right? What in effect happens is that as long as the sample is only a small part of the population, then it's only the size of your sample. So it is kind of like tasting. It is pretty much like tasting. You don't need a bigger taste just because you have a bigger glass. Remember I gave you imagine you're making a big soup, a huge soup, and you have all sorts of good ingredients in it, like onions and carrots and peas and everything. As long as you stir it up and randomly mix it, and you're tasting it, you don't need, even if it's a big pot, you don't need to take a giant amount out of it to taste it. You can just take, just enough so that it's well mixed and you get a sort of feel for all the different things in the soup. Whereas if you're making a little pot of soup, probably about the same taste would be, you don't need a bigger taste from a bigger soup, do you? And if it's a really well mixed sample, like your blood, you don't go into the doctor and say, hey, I'm a giant person. You better take a lot of blood from me. Or you take a little baby in, and then you wouldn't say, oh, the baby only needs a tiny little drop because it's a little baby. No, the blood sample is about the same size for everybody, no matter how much they weigh or how big they are. So that's the idea. All right, any questions on that? All right, so now the idea is what? It's only the size of the sample. So a bigger sample will give you more accuracy, but it doesn't depend on the population size that it's coming from. We're never going to use this n in our formula, in our standard error formula. We're only going to use this, the size of the sample. We never use that in our standard error formulas, unless we're sampling more than 20% of the population. All right, so where did we leave off? Let's see. I think we went up to page 193. I think we're on page 193. And we're going to continue with looking at sampling, taking how sample percents estimate population percents and attaching standard errors and then building confidence intervals. That's what we're doing in this chapter. So here's an example. So a CNN poll of 1,250 people, randomly selected people across the whole nation, asked the following question. Do you like to watch reality-based television programs or don't you? So 43% of the people in the sample said yes, they do. How many people here like to watch reality TV shows? Let me just... Okay, you want to do that one as an eye clicker? Yeah, okay, so take out your eye clickers while we look at this. So 43% So the 43%, we'd call them ones. And if I gave you 3 categories, like I will in a minute, with the eye clickers, yes, no, and not sure. What do we do with 3 categories? With all yes and no questions, all percent problems have been translated into just 2 categories. We either have something or we don't. It either is they either say yes or they don't say yes. So what we're going to do is we are going to collapse these 3 categories into just 2. So they either say yes or they don't say yes. This is not yes. In order to use the normal curve, we have to do that. Later in the semester, we'll look at how to analyze problems that have 3 different categories. But for now, if we want to use the normal curve, we just have to change them into either yes or not yes, or ones and zeros. Okay? So you must collapse these 3 categories into 2 to use the methods the standard errors that we've developed. So you must collapse the 3 categories into 2 categories in order to use the standard error formulas, which are based on the normal curve, the central limit theorem, into 2 categories to use basically the normal curve to build these confidence intervals. All right, now why don't we do the eye clicker question and see how you compare to the 43%. Okay, so let's go to here and let's start it. Do you or like to watch reality-based television programs or don't you? A, B, or C? We'll go to 30 seconds here. This is the smallest our class has ever been, right? Oh my goodness, okay. It looks sparse, all right. Unbelievably small, I can't believe it. Okay, stop. So, let's see what you said. So 55%, so which is higher than 43% nationwide, so the majority of the class likes to watch reality-based TV. Okay. We have more girls in this class. It's like 2/3 girls, and I think girls like to watch reality shows more than guys. If this was sports programs, we would have gotten more guys probably. Okay, now let's go back to the camera and figure out a 95% confidence interval for the percent of all US adults. Well, we're going to base it on this sample, of course, not on what we said, and it would be 43% plus or minus what? How do we figure this out? Do you remember? Do you remember what a 95% confidence interval is? We're going to have to attach some margin of error, and what do you think it is? 2, because that is between 2 and -2 on this normal curve, 95% of the area. Why we're using plus or minus 2 is because between 2, and here's some true population percentage right there, and 95% of us, if we sampled from the whole population, 95% of the time will be within 2 standard errors of the true population percentage. So we can be 95% sure we're within plus or minus 2 standard errors. All right, so what is that? We've got to figure out that standard error for the percent. How do we do that? What do we do? Do you remember? Let's see. This standard error for the percent, what's it going to be? Let's say it's going to be 43 plus or minus 2. Now, standard error for percent, it's going to be, let's do it way up here. It'll be SD of the box, of the whole population, divided by the square root of n. And then we're going to just multiply by 100. Now, SD of the box. Well, we don't know what's in the whole population, but we estimate that from our sample. The SD will estimate from our sample to be what? To be, do you know, the square root of what? 0.43%, we'll say 0.43 times what? Do you know? 0.57, excellent. Divided by what? The square root of, now what's n? Is it going to be the millions of people in the population or the 1,250 people in our sample? 1,250 people in our sample, and then times 100. That's what we have to figure out. So let's take out our calculators and do it, because I really want to get you prepared for this exam that's coming up. And so many people know how to do this, and then they make these stupid calculator mistakes. So just be sure that you don't do that. Get out your calculators with me so you can make sure you don't make these dumb mistakes on the exam that I see all the time. So get out your calculators. The more time you spend here preparing for the exam, the less time you're going to have to spend at home. Okay, so I just wanted, the best way to make sure you don't make any careless errors is to first compute this. Let's get this part right here, okay? Because we know that that part, the square root of 0.43 times 0.57, this standard deviation part has to be between what and what? It has to be between what and what? 0 and what? 0.5. And this is going to be very close to 0.5. Let's see what it is. See, it's 0.495. So first check that out. If you got something over 0.5, you know you did something wrong. The biggest it can be is when you have a 50-50 split. That's the most uncertainty. So that's the biggest, 0.495. Okay, so that's what we have here. Now we're going to divide by what? We'll divide by the square root of 1250. So let's do that. And now that's the decimal. We want to change it to a percent. So we multiply it by 100, and that's our standard error. And if you notice, it's a good thing to notice, because you're going to be reading the newspapers and looking at these polls all the time. And just about always, you'll see a margin of error of 3%. And you'll see where that comes from. So far, one standard error is 1.4%. That's this part. But a margin of error that's reported in the papers is always 2 of these. So this is 1.4 right here. We can write that. So that's 43% plus or minus 2 times the 1.4%. That's what we've got here. All right, so we're going to multiply this by 2. And now we get 2.8%. Very close to the 3% that usually is reported. In fact, they usually just round it to 3. Because public opinion polls are usually about 1,000 people. All right, so plus or minus 2.8. So what does that mean? That's 40, this is our range. We can be 95% sure that if we polled the whole population, it would be in the range of plus or minus 43% plus or minus 2.8%. Plus or minus 2.8%, 2 of those. All right? So our upper limit would be 43 plus 2.8, which brings us up to 45.8, and our lower limit would be 43 minus 2.8, which brings us down to 40.2%. So that's our confidence interval. Does everybody understand that? Questions? Everybody understand that? Okay, good. Now, the CNN poll asks a bunch of dicey questions. Before you look at what their answers are, let's do the same thing in class, just because it's fun to see how we compare. So let's look at, oh, sorry. Okay, I'll go back to the document camera and see, make sure that comes up, because something disappeared. I tell you, I am jinxed. All right, I want to ask you this question, so I'm just going to try to go back to the PC Let's all just have wishful thinking here. PC work, PC work. Yes, it did. All right. Now, would you be willing or not willing to allow a reality-based TV show film you? Let's start with this one, being in your pajamas. This is the one you're answering. Starting it. Just this one. That's the one we're doing. We're going to do some other ones too, but I just want to, we'll start with this one. Oh, now all of a sudden we have more people interested in answering the question. All of a sudden people are chiming in. Look, 224. Were you guys asleep before? Oh my goodness, it's going up and up. All right, I guess this interests you. All right, 240. Oh, come on, are you done? 250? Okay, we're done. So now let's see how you answered. Oh, overwhelmingly, you guys would like, wow, 69%. Now look in your notebooks. Look at the bottom of the page. Look what the nationwide poll said. You guys are so different than the nationwide poll. The nationwide poll said only 31% would be willing to do that. And you, young people, say, why not? Pajamas, you know, some of you might, I don't know, haven't you? I've worn what I've slept in to come to class before, and I'm up here. These aren't my pajamas, though. Okay. So now let's do the next one. Or how about kissing? You tell me where to stop. Where do you want, what's the next one you want to do? This, which one? This one or this one? Being drunk? Okay, being drunk. That's a hard one. Would you? Being drunk. Okay, let's try it. That's an interesting one. Okay. That's the one we're doing, being drunk. Would you be drunk on nationwide TV? The thing is, once you're drunk, your judgment's off. So probably, if you're really, you know, some camp person, once you're drunk, you know, coming at like Girls Gone Wild, all those girls are drunk, and then they're doing all sorts of things. Okay. All right, let's stop it. But you're deciding sober whether this would happen. So let's see what you said. 52% said no, but 40% said yes. Let's compare it to what the nation said, or what the nationwide sample said. If we look down, it's only 16%. You guys are much bolder. 40% said yes. Okay, interesting. All right, now let's move on. And let's look at the next one. All right, which one do you want to do next? This one? No? Naked? Okay, naked. That's a good one. Being naked, boy. Answer honestly. Would you really allow yourself to be naked on nature? Well, once you're drunk, you know, if you did a conditional probability, given that you're drunk, then would you just lift everything up? Okay. But we're deciding sober here. Okay, so we're stopping. And let's see, I'm really curious. Oh, only 12%. Oh, which are the 12%? Can we want to raise your hands? Anybody want to say? All right, okay, 2 guys here. Any girls? 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 Okay. All right. You probably all have really good bodies. Okay, now, all right, we're going to go to the next one, and here's the last one. Having sex on nationwide TV. We're starting this up. Why not? Somebody said. not. It could just happen. Oh, a lot of people want to weigh in on this one. Woo, you got it right up there to 200, like in no time. 10 seconds you got up there. All right. Okay, so I think that's everybody. We're going to stop it. And here's the big reveal. Let's see. Okay. Only 11%. What's this? D and E. It's like, whoa, that idea was just so whoa, beyond not sure. Okay, so this is 11% said yes. More people would be, wasn't it only 8% for naked? Oh, it was 12. So it's almost, I was thinking some people might have had to sex as long as they had their clothes on. But, but that's 11 and 12, wow. So it's like, it's probably the same people, but maybe one person dropped out, 2 people dropped out. 26 people said, okay, 26 people, let's see, I want to see. Don't you want to raise your hands? I mean, if you're willing to do it on nationwide TV, you can tell Stat 100 about it, right? Raise your hands high. Be proud. I just want to see the girls too, if there are any matchups. Sorry. Stat 100 matchups could be. Okay. All right. That actually happened once in one class. There were only 2 people who raised their hand. This was a while back, and it was a guy and a girl. And they were the only 2 that's, now you're being much more honest. And they looked at each other from across the room. One was over here and one, they're kind of checking each other out. And then afterwards, after class, I saw them talking. So romantic. Okay. So I don't know what happened there, but okay, so now I think we've done all these. Let's go back to the document camera, and we can see the point is that when we just have this sample that's not random, it can be wildly different than what, a random sample from the whole nation is going to be a better reflection of what the whole nation thinks than just some collection of people like us, right? Because here's what the sample said. Wow, only 5%. We had 11% here, 12% here. For being drunk, what was us? I can't remember. 12. For drunk? 52? Oh, 40. It was 40%. Yeah, so we're higher in every category, especially in the pajama category. Well, in all of them, we're much higher. Okay, really interesting. So now, we looked at the rest of the questions, and which question, this is kind of tough here. This is a sort of hard question, but see if you can get it. Which question has the largest standard error, and which one has the smallest? Do you think they'd all have the same, like they all have the same sample size? So if we look back here, this is the standard error. They all have the same n. Do they all have the same standard deviations? Let's look. Do you think these would all have the same standard deviations? Remember what the standard, let's just do this one, you'll see what I mean. So the SD of this one is going to be what? The SD would be what? This SD, and let's look at this. So this SD is going to be the square root of 0.31, and then we have to group these together as zeros. So times 0.69, and this SD, let's just go to the very end of this one. This SD is equal to, SD equals having sex. Now that's going to look really weird in your notes. That's the definition of SD. Oh, it's written in my notes. SD is having sex. No, I'm sorry. I meant right here. This is what I mean. It's embarrassing. Okay, this is the square root. It's equal to the square root of what? 0.5, is that what you said? Tell me what's, I'm going to write it wrong for a second just to show you something. Okay, so this is what people do on the exam all the time. When they see 5%, just make that careless error. Please don't make that careless error. And you'll be able to detect it right away, because when you did your standard deviation, look what would happen if you did that. I just don't want anybody in class today to make this mistake, because it happens all the time. So if you did this, See, you get something higher than 0.5, so you'd know right away you made a mistake. Don't do that. It's what? It's the square root of 0.05 times 0.95, and that's going to be small, because it's going down. What if it was 0 times 1? It would be 0. This is making it smaller, the error, and here you get only 0.217. Okay? So this 0.05, this is about 0.217, and this one is going to be the larger one. This is going to be much closer to 0.5. Let's just do this, and then we'll be able to answer our question. Sorry. So this is 0.31 times 0.669, and that's 0.46. Okay, so this has the largest SD, and this has the smallest SD. So that means that this is going to have the largest standard error, and this will have the smallest. The closer you get to a 50-50, the largest the standard, you'll have a larger standard error when you have more of a 50-50 mix, because that's 50-50 split. Okay? So let's go up here. And which question had the largest and which had the smallest? So pajamas has the largest. And which is the smallest? Having sex was the smallest. There just isn't as much uncertainty because variability in your sample. Because most people would say no to this. Having sex has the smallest. Okay, good. Suppose you computed 95% confidence intervals for each question. Would the intervals all be the same size? Would they? What do you think? Would they be, like, would you attach the same margin of error? No, because your standard errors are different. So they'd be the biggest with the pajamas, you know, with the biggest standard errors, and the smallest, you'd zero in closer to your answer with the smallest standard deviations, with the smallest standard error. So no. So what, we can even figure it out. PJ's, so PJ's 95% confidence interval would be what? It would be 31% plus or minus 2 times 2 standard errors. So it would be 2 times, let's just do it on the calculator. I want to get you used to doing this on the calculator. So it would be 2 times, whoops, I just had it, I'm sorry. 0.46 divided by what? The square root of what? You tell me, square root of what? That's the standard deviation divided by the square root of n, which is square root of 1250 times what? Okay, so that's 1.3. Let's put that right here. All right, and how about for the other one? Having sex is going to be the smallest standard error. That would be a 95% confidence interval would be 5% plus or minus 2 times its standard error, which we've already got the standard deviation was 0.217. So let's follow through from there. We have 0.217 for the standard deviation, and then what am I going to divide by? What am I going to divide by?
Same number.
Yeah, right there. And so what does that give me? And then I have to multiply by what? 100? It's only 0.614, okay? So that's smaller. It's a much smaller. All right, so the standard error depends on 2 things. The standard deviation of the box, which is really not that variable, as you can see. It doesn't vary that much, even when you have a really lopsided thing. Okay, but what it will vary with the sample size. As we said, not the population size, but the sample size. The bigger the sample, are you going to get more accuracy or less? If we increased our sample, do you think you're going to have more error or less? Less, you're going to have more accuracy. by what? So if the sample size was 5,000 instead of 1250, how would your confidence interval change? Well, let's think about it. So if n increases by what? What is that? 1250 times 2 is 2,500, so it's times 4. So if it increases by multiplying by 4, what am I saying? I'm going from 1250 to 1250 times 4. Then what happens to your confidence interval? Well, it's just, you're going to zoom in on your answer. Your error is going to go down, so your confidence interval is going to get narrower. So then the standard error for percent will go down. You'll have less error with a bigger sample size. By what? Do you think it's by dividing by 4? What's wrong with that? Do you think it's going to go down by a factor of 4? Look at our formula. It's going to go down by a factor of what? Not a factor of 4, but by a factor of square root of 4. Do you see that? Our formula, it's going to go down because we're dividing by the square root of n. So if you multiply n by 4, you only, okay? So it'll go down by the square root of 4, by 2. Okay? So the confidence interval would be shortened, would be, you wouldn't have you'd zoom in more by, it would be cut in half. The width of the confidence interval would zoom in more. You'd have more accuracy with a bigger sample size. Does that make sense? What do you think? Is that hard to understand? You wouldn't have to touch such big margins of error. Okay? So the confidence interval would be what? What should I say? Divided by 2, cut in half. What do you want to? Would be half as wide? So the confidence interval would be what? Divided by 2? The width of it? Would be divided, the width of the confidence interval would be divided by square root of 4, would be divided by 2. So the width of the confidence interval. Zoom in on your answer, okay? The bigger sample size. Does that make sense? Yeah. So the sample size matters, the population size doesn't. All right. Now, all right. So, let's see. The next thing in your notebook is this sort of how many people to poll to get certain margins of error. Why don't we skip that for now and instead just continue exactly what we were doing with with percent problems, and we're going to look at problems that you answer, questions with numerical answers. But first, it's a new chapter. Let's take a breather, because I can see people are kind of restless. So, anybody have a story, joke, anything? Anybody want to do any entertainment? Because I feel like sitting down for a second. You have something, what?
Right. Who watches Family Guy? All right.
You want Mike? You want? Just put that on your ear and hold this.
All right.
Yeah.
You hear me good? All right. Someone give me a character. Thank you. How you coming on that novel you working on? Huh? Got a big stack of papers there. Got a nice little story brewing there for your bigger novel. You've been working on for 3 years. Huh? Got a compelling protagonist. All right, y'all remember the episode where Peter got into a conflict with Carter Peterschmidt because he lost all his money? All right, who watches Dawson's Creek too? Well, whoever did, okay. Y'all remember the theme song for that? All right. I don't want to wait for my lunch to get colder. Why can't I eat it now? I don't want to wait for a new Toyota. I want the car that's got a lot of gas. Quagmire? All right. Here's the condom I thought I put on. Aren't I just the worst? Give me another character. All right, I'm hearing Brian. All right. What's a dog got to do to get a martini in here? All right, I'm gonna do an unsuspected character that y'all never thought I would do, but I'm gonna do the character known as Bruce. All right. Y'all best be careful. I'm gonna sting you with my stinger. Oh no, but then it's gonna die if I sting you. Oh hey, you said my name. I'm just happy that I met somebody today. Someone at the bookstore. Someone who shares the same literature as I do. Oh, and the adventure begins again. Another unsuspecting character you might have not thought of is Ollie Williams. Good evening, I'm Tom Tucker. We now return to Ollie Williams with the Blackie Weather Report. How's the weather, Ollie? It's raining sideways! Sounds rough, Ollie. Sounds rough, Ollie. What do you think about that? Where's your hat? I had one! Where is it? Inside out, 2 miles away! Is there anything that we should bring you? Bring me some soup! What kind? Chunky!
Do the old guy.
Old guy? Oh, Herbert the pervert, okay. Oh no, there's no police here to help me. I hope they don't find my money strapped to my thigh. No, 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 no! I can't feel my legs. Welcome to the party, pal. Oh wait, there they are. Oh. Thank you, I'm James Totten, by the way.
Thank you so much. Oh, it's great. Oh, okay. I really appreciate that. Gave me a little break. Okay, so now we're all ready to start chapter 18. And let's look at what chapter 18 is. It's just like what we just did. We're just going to keep looking at surveys, but this time, instead of modeling them with 0-1 boxes, we're going to look at questions that have numerical answers. Like, for example, instead of asking like, did you sleep at all during my lecture, during this past lecture? Yes or no? Raise your hand if yes, if you slept at all. Okay? Or no. The rest of you, that's a yes or no. Instead, I could ask, like, how many minutes did you sleep? And then you'd answer with a number. And so we wouldn't have percent. Our relevant statistic would be an average, all right? Because we'd look at all the numbers. So here's a question. So we're going to be looking at surveys that ask questions with numerical answers, okay? Like, how much did you sleep through the lecture? Or how much do you weigh? Or how much money do you have in your pocket right now? Or how many people have you ever slept with in your life? That's what this question asks. So ABC News asked a random sample. This is kind of interesting because they asked a random sample of 1,600 straight men and 1,600 straight women nationwide the following question. How many total sexual partners have you had in your entire life? And the rounded results, because if you took an average, it wouldn't necessarily be a whole number, right? The rounded results were these. The men said they slept with a lot more people. 20 was the average. With a standard deviation, there's a typo here. This should actually be 16. So a standard deviation of 16. So in other words, some people said it's a big standard deviation. because some people answered like really high numbers. Now, with the women, it was more moderate. It was 6 people in their entire life with a standard deviation of 4. All right, I'm not going to ask this class, I won't ask you this as a eye clicker. For one thing, you're too young to have accumulated many partners, I hope. Well, I don't care, but okay. Now, we can estimate the average number of sex partners all American men would report having to be what? So we're doing the same thing. If we take this survey because we want to know how the sexual behavior of the entire population, what would be our best guess? If what men answered was, if our sample was 20, I mean, the model is this, the idea is this. We want to know what all the millions of US men and millions of US women would answer to this question. But we don't have the time and the resources to sample them all. So if we wanted to model it, the probability model would be that we'd have millions of tickets in this box, millions of tickets, and on each has to be written a number, and the number would be how many people they slept with, what they would answer. So millions of tickets on each is written, you don't have zeros and ones because it's not a yes and no question. With a yes and no question, we modeled it by saying the yeses are ones and the nos are zeros. But now millions of tickets on each is written a number, not just zeros and ones, a number ranging from, the smallest would be what? You can't sleep with a negative number of people, so the smallest is 0. And the largest to approximately, I don't know, what do you think the largest anybody would answer would be? 50? I think it's larger, just judging from 50, you think? I think it would be larger because there are people like basketball. Remember that Wilt Chamberlain guy who said he slept with over 1,000 people? 2,000? I mean, you'd lose count way before that, wouldn't you? Okay. 200? 100? I think some guys would say maybe even more than 100. I'd say approximately, they're lying, some of them. It's not what they actually did. It's what they would respond. It's not what they actually did. Because you're asking a sexual question, and how many people are honest, and how many people brag, and how many people lie. So what do you think it would be if men, think about how men can brag. 50? I think it's more. I'll say raising to about 200. Okay? All right, that says to approximately. That's what that means. Range, that's what that squiggle means, to about 200. So there's less, so you got the idea. Now, we don't know what the average is, because we don't know what's inside here. If we did, we wouldn't be taking a survey. So we have no clue. And we have no clue here either. That's why we take a survey. So we pull out these tickets, and we randomly sample, poll 1,600 of the millions of men, and the average among the 16 people is what? And the sample average, the average there, turned out to be, that's what we have right here, 20, with a standard deviation in our sample, with a sample SD equal to 16. All right, that's what we've got. So now, what I did here is so we can estimate the average number of all American would report having to be what? If our sample average is 20, don't you think that's going to be our best estimate for here? Don't you think that will be what we'll estimate? We'll estimate 20 from our sample. Because what else would we do? Why would we estimate anything else? Would you go higher or lower? I mean, your sample says 20, so why not estimate 20 for what everybody would say, right? It's just common sense, isn't it? All right, so this is just no-brainer. Why would you estimate anything else? That's the average, we think. A lot of people would be higher, a lot of people would be lower, but that's the average. Okay, so now give or take what? This is the hard part. Like every time we take a sample, it's going to be slightly different because we're going to get a different group of 1,600 men. So it's going to bounce around. And how much it bounces around by is called the what? The chance error or the standard error for the sample average. So what we want to put in right here, right there, is going to be the standard error of our sample. The standard error of our sample average. Because our sample is going to change. Each time we do it, it would change. The population supposedly is fixed. You know, if you asked everybody, it just stays the same. But then you take a different samples, you get different people, and that bounces around. So the error of our sample average is what? Now, how do we figure this out? Do you remember? Standard error is like a standard deviation. So we've got that much. Standard deviation of the box. Divided by what? Our sample size. Not the population size, but the sample size. So that's going to be 1250. What's this going to be? This is the standard deviation. What is it going to be, 16? Yeah, you're right. But why? Because this is really standard deviation of the box here. But what we're going to do is we're going to use this 16 and we're going to estimate. We're going to estimate this to be 16, the same as our sample. We're going to do that. And you know, it's going to change depending on our sample. And we said it was a good estimate with zeros and ones and a percent problem because the standard deviation of zeros and one doesn't change very much. It's usually very close to 0.5. But this could change a whole lot. Think about it. If you just sampled some people, you might get somebody who said 200 or a few people and then would have a big standard deviation. Or your sample might more likely wouldn't have anybody who went up that far. You know, probably it would just be limited to people around, oh, I don't know, between 0 and 30 or something. You probably wouldn't get those really extreme ones. So you're probably it's not going to be a good reflection unless it's big enough. You can't just sample a few people. So what I'm saying is that we don't know the standard deviation of the box, so we're going to use the standard deviation of the sample, but it's not going to be good unless the sample size is large enough. When our sample is small, like just we sampled less than 25 people, we're going to have to adjust this estimate. Okay? And that's where that weird formula for, you know, you divide by the n-1, we take an average by taking the deviations from the, you don't take the, you square all your deviations, and then you don't take the average of them, you actually take n-1. Some of you learned that formula before. That's where we're going to apply it. But for now, we have a big enough sample, so this is good. So what you said is great. So this works because our sample size is larger than 25 here. So we're going to say, we're just going to use 16 over the square root of what? Not millions, but what? 1,600. So this is 16 over 40. Right? Which is what? 4 over 10. So that's 0.4. Boy, does that look small. Doesn't that look really small? 20, give or take 0.4. So the average doesn't bounce around that. Look at that. That's a very small, the standard error of the average is much smaller than the standard deviation. It's not like the range of the people are going to range from like 0 to hundreds, but the average, if you take a sample of 1,600 and take the average, then you take another sample of 1,600 and take the average, then you take another sample of 16, you're going to get about 20, give or take, just plus or minus 0.4. You're not going to get hundreds or 0 or anywhere close to that. You're not even going to get anything like 15 or even, it's going to be very unlikely to get 21. Or even 19. Isn't that sort of amazing that the average is going to be that close? In fact, we can build a 95% confidence interval by taking how many of these? 20 plus or minus what? How many of these would be our 95%? We can be 95% sure. If we polled everybody, the average of the whole population would be 20, give or take what? Do you see it? Here, let's turn the page. Maybe I'm just talking too fast because I wrote it down here. Okay? Now we can use the normal curve to build confidence intervals around our estimate, because the probability histogram for the average of a large enough draws will follow the normal curve, even if the data doesn't. The data itself clearly doesn't. It couldn't possibly, because we had a standard deviation of 16. So it's really skewed to the right, because so many people are going to answer really high. I mean, if the average is 20 and the standard deviation is 16, that means people answered much, some people answered really high numbers. It's skewed to the right. It couldn't possibly be normal, but that doesn't matter because of that beautiful central limit theorem. It says that the probability histogram for the average will follow the normal curve, as long as you have enough draws. So a 95% confidence interval, is going to be our sample average, which is 20, plus or minus something times the standard error for the average. Now this something right here is going to correspond to 95%. It's going to be between the z-score of what and what on the normal curve? 2. Great. Plus, what I'm doing, I'm just doing on the normal curve between 2 and negative 2 is 95%. So 95% of the time we're going to get a sample that's that's within the true population average, within plus or minus 2 standard errors of the true population average. Some of us will get outside those limits 5% of the time. All right, so let's do this. So there's where our 20 comes from, plus or minus what? 2 times, now how can we just figured that out. It was on the previous page. Remember what we got? 0.4. So that's going to be 20 plus or minus 2 times 0.4, which is plus or minus 0.8. So, wow, that means we can be 95% sure that if we pulled every single guy in the US who's heterosexual, we'd get between what would we get? 19 point what? 2, an average of 19.2 and an average of what? 20.1. Isn't that surprising to you? That we can be 95% sure we'd be that. Okay, that's pretty amazing. So how about for women? What would we do? Can you fill this in for women? It would be what? 6 is the average. The sample average is 6 plus or minus 2 times. What's the standard error for the average for women? It's SD over the square root of n. And what's the average? What's the SD for women? We have to look back at the previous page. 4 divided by, there's also 1,600 of them. So that's 4 over 40, which is 0.1. They had a smaller standard deviation because not as many women are going to say hundreds. Okay, so that's plus times 0.1. So that's an even smaller confidence interval because the standard deviation. Women aren't going to be so extreme in their answers. Plus or minus 0.2. All right, so what do we get? So what's our confidence interval then? We can be, it's going to go from 6 minus, we'll put the lower number first, 6 minus 0.2. So if we pulled all the women, their average would be, the average of all the millions of women would be between 5.8 and what? 6.2. That's really not a very big range, that we can be 95% sure of that. All right, now, which of the following statements is true? You have to think about this, okay? Think about, we drew the sample from the whole United States. So, a 95% confidence interval, we're just talking about men here. So we drew it from for the average number of sex partners, all straight US men actually had. Look at this actually. Do you think we could be sure that what they actually had is what they said they had? Do you? Common sense. What would you guess? No. So what are you going to say for this one? False or true? False. How about this? Which one? How about this one? A 95% confidence interval for the average number of sex partners all gay U.S. men would say they had is. Can we apply it to a different population? What we got from straight men? No, so this is false. How about this one? A 95% confidence interval for the average number of sex partners all straight U.S. men would say they had is this. Does this look right or not? Is this? Yeah, this is the only true one, I think. What's the next one? Because this is exactly what the confidence interval applies to, the population that it was drawn from. How about this one? No. All rural U.S. men, we don't know, it might be, but we have no idea if rural men are the same as men who live in cities. So this is false. Okay, let's look at this. If we assume a population with roughly the same number of men and women and that all encounters are heterosexual, is it mathematically possible for them to have as different averages as they claim? This was reported in the popular press, and they said, well, they said it was, but do you think it is? They said they could have the same averages. They said the medians would have to be different. Which do you think? Do you think the medians would be different, or the average would be different, or neither? Anybody want to comment on this? Do you think it's possible that they could all be telling the truth? Let's think about it. How would you even go about this? I mean, the way I would go about this is I'd just try to think of it like, pretend there are only 10 people in the population or something, 10 men and 10 women, okay? And then just see if it works for that. So imagine 10 men and 10 women. And then let's just think of a real extreme case where it's really different between the men and the women. Let's see. What would be the most extreme case? What would be the most a man could sleep with? And if there's only a population of 10 and 10, the most the guy could say is how many different women he slept with would be what? 10. So let's say one guy slept with all 10 women, okay? So imagine 10 men and 10 women. I'm just trying to see if the averages would be different. So one man, like some player guy, sleeps with all 10 women. And we'll take the extreme case. And then let's say none of the other guys sleep with anybody, okay? And the other 9 have 0 partners. I'm just trying to make a really extreme case. Okay, so there's 1 10 and there's 9 zeros for the guys. All right? Now for the women that would mean what? So then each woman would have to sleep with what? If that was the case, each woman would be determined, right? Exactly. Each woman only slept with that one guy. So every woman would have the same. So each woman would have to answer, each woman sleeps with just that one guy. Okay, so this is the most extreme it can get, and let's see if the averages are the same. So what do we have here? I need another piece of paper. Oh well, I'll just bring it over I'll just do it over here. Okay, so for the men, the average for the men would be what? The average for the men is like what? 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the men. So the average, 10. That one guy. Woo, he's a happy guy. This is one guy. Yay! And all the other ones are sad. Okay, so the average for men would be what? 10 divided by 10, which is 1. How about for women? This is the men. For women, what do the women look like? They're all the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the average for the women would be what? 10 divided by 10, which is 1. They have to be the same. They have to be the same. So somebody's lying, probably both. Or maybe they're not really lying, like the men are counting, like, they had some kind of encounter, and they say, yep, that was 1, and the women are saying, doesn't count. You know what I'm saying. Okay, so how about the medians though? This is kind of interesting. Median for men would be what? What's the median for the men? The middle number, 1, 2, 3, 4, 5, there's your median. The median for the men is what? 0. These can be different. The median for the women would be what? 1, 2, well, it's just 1. So that can be different, but not the average. Okay, so now, if we want to finish up today, we have to go back and do one more thing. So you game? All right, it's choosing how many people to poll. And so the math is a little bit, I hope you can follow along. Let's go and try it. It's not too bad. I'll try to make it easy for you. So that is back right here on page 194. It's what we skipped. How many people already know how to do this problem? Because I've already assigned the homework. Raise your hands. Okay. Well, all right. So let's read what we're doing here. So we say, you all know that the more people we poll, the more accurate our sample statistic is. Our error goes down with the more people we poll. We've already looked at that. You know that by the square root of n. All right. So let's say you're working for some polling organization, and they say they want you to get a margin of error that's about 2% or 4% or 5% or 10%. And they say, how many people do I have to poll for those margin? You say, well, how many people? If you want real accuracy, 1%, you're going to have to poll a lot of people. If they don't care that much about the accuracy, 10% margin of error, then you can poll a lot fewer people. But how do we figure out exactly? So let's think about it. How many people do we need to poll to a 95% confidence interval? All right, and with a margin of error of this. Okay, so a margin of error for a 95% confidence interval is what? It's going to be plus or minus 2 times the standard error for percent. That's what it's going to be, right? 95%, you're going to take your sample percent and add that margin of error plus or minus 2 standard errors. So, okay, so what does that mean? Whoa, so the standard error for the percent is what? It's the standard deviation divided by the square root of n times 100. And we're going to have to solve for n for different margins of errors. That's what we're going to have to do. Now, first thing, let's just assume that that standard deviation is 0.5. We'll be really conservative. So unless otherwise told, let's always assume, unless otherwise told, that the SD is equal to 0.5. Because it's usually really close to 0.5. You have to get to a really lopsided poll before it gets down. Okay? And that's the conservative estimate. All right, so assume unless otherwise told. So now, what does that mean? If we put 0.5 in here, this works out to be what? 2 times 0.5 divided by the square root of n times 100. Whoa, let's just get from here over to here. I mean, this is all this stuff in between. This is what we have. So we have our margin of error, which could either be 2%, 4%, whatever, is going to be equal to, what's 2 times a half? 1. 1 times 100 is 100. So it boils down to that. There's our formula. And now for 2%, we'll just plug that in. Or 4%, we could plug that in, whatever. And then we can just solve for n. But solving for n in the denominator is kind of a hassle each time. So why don't we solve for n right now? Okay? So let's just solve for n right now. Let's put n in the numerator. If you put n in the numerator, the square root of n, what does that work out to be? That would be what? You could multiply those two, or you could say square root of n over 1 is 100 over n. It would be 100 over, I'm just putting it in the numerator, by multiplying both sides by the square root of n and then dividing by margin of error. Okay? That's just a algebra. Any questions? You can just multiply those two together, and it's like, multiply those two together. All right. Now, that's still not n. What do I have to do to both sides? Square them. So I'm going to square both sides, and then I'll get my formula. N equals 100 over the margin of error squared. All right, so now for a 2% margin of error, all I have to do is put 2 here, and I'll get 50 squared. For 4%, I'll put 4. The bigger the margin of error, the smaller the sample size. So here, I'll say n equals 100 over 2, which is 50 squared, which is 2,500. Now, if I'm willing to settle for a much bigger margin of error, then I'd say 100 over 4 squared. And I'd get what? 25 squared, which is 625. Let's do one more. How about for a margin of error of, if you're willing to accept a margin of error of what, name something. 10%, 5%, what do you want? 10%. 10% margin of error. If you're willing to accept a 10% margin of error, how many people? Then you'd say n equals, well, that's a huge margin of error. So you don't need many people. So you just say 100 divided by 10, which is 10 squared. So you'd only need to sample 100 people if you're willing to accept plus or minus 10%. Okay, so that's pretty much, all right, now the very last question is, what if it was like a 20%, 80% split in the population or something, or that would give us a standard deviation of 0.4, not 0.5. So let's say it wasn't a very close, between yeses and nos wasn't close. So instead of putting a 0.5 in here, if we had a really lopsided population, we'd have a smaller, we wouldn't have to sample as many people. So let's put a 0.4 in there. Where would that change things up? It would change it up right here. Instead of getting 100, we'd get what? 80 here. So let's look at that. So we'd have margin of error. We'd do the same thing, but we couldn't use this formula here. We'd have to say the margin of error is going to be equal to 2 standard errors for percent. Okay? We'd have to go back there and we'd say, okay, 2SD times the square root of n times 100, which is 2 instead of the point. Now, they said, what if the standard deviation of the population was 0.4? So we'd say 2 times 0.4, not times 0.5, over the square root of n times 100. So where that would change things up is right here. You'd get 80 over the square root of n is your margin of error. And then if you solve for n, you'd get the square root of n over 1 is equal to 80 over the margin of error, right? So you'd get, now when you solve for it, you get square root of n over 1, square root of n over its, I'm just saying square root of n over 1 would be equal to 80 over the margin of error. It's just algebra. And then I'd square both sides, and I'd get n equals, instead of 100, it would be 80 over the margin of error squared. Okay? So now, what does the question ask? To get a 4%, now you can plug in whatever you want. So here's our formula. N equals, instead of the 100, it's 80 over our margin of error squared instead of the 100. This is when you have an ST of 0.4. So now, for a 4% margin of error, we'd have, instead of having 100, instead of having 625, we're going to have less. We're going to have 80 over, instead of 100 over 4, we're going to have 80 over 4 squared. So that would be 20 squared. So you wouldn't have to sample 625 people because there wouldn't be as much uncertainty. You'd sample only 400 people. And if it was a margin, if it was only 0.3, like a 90-10 split, it would be only 60 squared. Okay? 360 people. All right, that's it. Next time what we're going to do is we'll review for the exam. I'll send you an email.